All right. Welcome, everyone, to this week's Autonomy Talks, exceptionally live. Today is a great pleasure to have Professor Paull, who is an associate professor at the Université de Montréal, and he's also the founder and co-lead of the Montreal Robotics and Embodied AI Lab. So something about Liam, he obtained his PhD from the University of New Brunswick, and then he moved to MIT, where he was first a postdoc and then a research scientist at CSAIL. And his research focuses on robotics problems, including building representations of the world, for instance, in applications such as localization and mapping, modeling of uncertainty, and building better workflows to teach robotic agents new tasks. He's also a co-founder and director of the Duckytown Foundation, which we know very well in our lab. This is an organization dedicated to making engaging robotics learning experiences accessible to everyone. So today's talk has an exciting title, Building Representations to Enable Robots to Complete Complex and Abstract Tasks. And we are excited to hear more about it. And I give you the stage, Liam.
Thanks, Charlie. And thanks for having me live and Zoom. It's very, very nice to be here. So I'm going to talk today about, maybe I'll start by just giving a little bit of an overview of the work that we do in my lab. Joelle sort of already introduced it. We're trying to, the themes that we explore are learning efficient representations, quantifying uncertainty, efficient robot learning and simulation. We also have this thread of benchmarking and evaluation. We apply these things to tasks like autonomous driving, SLAM, navigation, mobile manipulation. So today I'm mostly going to talk about the first theme, building or learning efficient representations. And we'll talk a little bit about SLAM and navigation for the most part. Okay, so maybe just to motivate things, I'll show this video. So this is now a very old video from Peter Rubeel with the PR1 robot. I think it's maybe 10 years old. And it's showing this PR1 robot doing all sorts of things that we would want a robot to do, especially a domestic robot. It's feeding us, it's emptying the dishwasher, it's cleaning up the house, et cetera, et cetera. So I guess robotics is solved, right? But the problem with this video, I guess, is that it's 100% teleoperated. Okay, but to me, that means that the hardware, at least it's sufficient, right? We have proof. We have an existence proof that if we could download the abilities from our brain into a robotic agent, that we could actually solve these tasks with this, what I would now consider relatively primitive hardware. We actually have much better hardware now. So I argue that the thing that's really missing is really the right representation and the right abstractions in order to be able to both be able to build these representations efficiently and then leverage them for reasoning and planning downstream. Okay, so I wasn't too sure about the audience, so we'll start with a bit of a brief overview of representations, because I'm mostly a SLAM guy, a perception guy, and this is like a mechanical engineering department, so I don't know if anyone knows what I'm talking about when I talk about SLAM. So I'll start about that, and then I'm going to explore sort of three themes: learnable representations, semantic representations, and topological representations if we have time. I want to spend most amount of time on semantic representations because in this work we're leveraging new large language and vision language models for embedding them in world representations. Okay, so bit of a brief overview. I think we're all sort of probably okay with the idea that we have these kind of traditional abstractions in robotics that we need to chain together in a traditional autonomy stack. On the one hand, we get sensor data and we have some kind of local sensing and perception. Hey, on the other end, we have to make some decision about how we act in the world. And in the middle, we have to leverage this, build this representation and use it to do reasoning, right? And so the key is actually, I would argue, is more important than the actual blocks themselves is actually the arrows, the interface between these things, right? So we have to somehow generate some representation. A full representation from our local perception system would be to just pass all the pixels or every single piece of raw data. But that's not going to work because it's not efficient, right? So we have this balance of being able to synthesize information from sensing, be able to build a representation about it, and then be able to use it for planning and reasoning. So what do I even mean when I'm talking about representation? So literally, I'm talking about how we encode the state of the robot in the world in the computer and how we actually use it to do algorithms. It might sort of seem at first that this is simple, but there's lots of examples that we can give where it's not so simple. So Imagine a picture where we have, okay, this is the same place in summer and winter. Like we need a representation that's maybe able to like reason about that. This is some kind of crazy high wire thing. This is a police officer doing some kind of like hand gesture. So there's lots of semantic meaning in what's going on here, right? And here we have weird perceptual aliasing coming from glass, right? So if we're just doing straight feature extraction, and maybe we would get totally fooled by this. Okay, so maybe a good place to start is like the desiderata for a good representation. I think there's some theoretical results on this. I mean, intuitively, we want something that's a sufficient statistic, i.e. it satisfies the Markov property, which means that it completely represents the world. More specifically, we want a sufficient statistic for the task that we're actually trying to achieve, okay? The task is crucial here. And finally, the optimal representation would be a minimal sufficient statistic for the task that you're trying to achieve. Okay, this is great in theoretical terms, but it's not very useful. In practical terms, we need representations that are efficient to compute and generate, that are efficient to use for downstream tasks, that generalize possibly across a range of environments or tasks that we may want to do, and probably as compact as possible, because this is going to enable the other things. Quick word about task specification. I mean, the way that we encode the task that we want a robot to do is in itself not a simple thing. Maybe we have the ability to specify like a goal point in space, but then we have to worry about like what frame that's in and then reconciling that into some kind of world frame, et cetera, et cetera. Much easier would be to specify tasks as either language or give goal images or other kind of like task specifications that have higher semantic meaning. There's also a lot more in the world than just geometry. There's semantics, by which I mean like properties of things. This is a piece of clothing. It's not just a point in space. And the fact that this is a piece of clothing or this is a desk actually, encodes some kind of meaning about what I can use for this. That's also connected to the affordances of specific objects. Like this, I know it's a piece of wood. I could, if it was Armageddon and I needed to stay warm, I could break down this desk and burn it and stay warm for some amount of time, right? Like that's one of the properties of wood, right? So I have that kind of level of like reasoning and my representation. And then finally, I think another piece that's important if we want to like deploy these robots into homes or consumer products is, does the construction of this representation actually require a robotics engineer in order to collect the data to generate? Or can we just like have some random person just sort of like driving the robot around and then that's sufficient for building the representation? Okay, so like 3-slide overview of representations in terms of just more technical detail. I think robot representations were probably pretty okay. Like we have SE2, we have SE3, we have, configuration spaces. We might have, other robots that are more complex, but I think we pretty much know how to model them, and that's probably the right representation for the robot. The world is much more difficult. So there's lots of options we can pick for how we're going to represent the world. So like, it's a bit ominous. So maybe we just represent it as a bunch of points in space. Maybe we represent it in a more dense way. Maybe it's not even metric at all. Maybe it's some combination of metrics and topology. These all have like their pros and cons, right? This, maybe it's good for localization, but I can't really use it for dense planning. This I can, but it's less efficient in terms of memory, whatever. We also have like dense representations in 3D that have similar properties, and I'll sort of talk about these a little bit later, but we could represent the world as like a dense set of point clouds. We could represent the world as a big grid of space in 3D, just like an occupancy grid map, or we have these other kind of implicit functions like sign distance fields that we can do. Okay, so that's what my view of the problem of what it means to have a good representation. So let's think about actually different possible representations that we've built in our lab or different tools that we built that have nice properties. So I guess maybe one thing to start in terms of, so in the context of learnable representations, is like, I consider this kind of like the great debate right now, is this debate of like, implicit versus explicit representations. And if you look on YouTube and all the like Google demos and everything, they're showing like amazing capabilities of robots doing like end-to-end RL. They don't have any explicit representation of the world there. It's somehow embedded in some kind of big neural network model that we can't really query, but maybe we don't need to. Maybe we can just do stuff based on this implicit model. So what I mean here is an explicit representation is one that we can actually interpret symbolically, and an implicit representation is one that's somehow learned and we can't easily interpret. And then there's like lots of hybrid options that have a little bit of both. So maybe I'll just start briefly by talking about a fun work that we did in our group. Now it's a few years ago, where we actually took the explicit structure of the way that we build these dense SLAM representations, and we just made the entire thing differentiable. And so like I argued at the time that like differentiability is the new linearity. Like actually we don't care, as long as you can pass gradients now, then you can put learnable pieces inside of your system kind of anywhere you want. And you can define errors anywhere you want. And you can pass gradients from those errors to those parameters. And so what we show in this work, and I'm not going to go through the nitty-gritty, it's kind of like what you end up needing to do this is just sort of like a bag of tricks, because there's only a few kind of classes of nonlinearities. Things like when you do switching, when you do stepping, like these are all like non-differentiable, not nice functions. And so you just need to like have a bag of tricks to generate differentiable versions of these functions. Like Levenberg-Marquardt is an example, right? There's like a switching parameter in there. And so instead of like a switching parameter, we need to turn that into like a smooth, for example. But yeah, so the idea here now is that, okay, so now I can differentiate through my entire SLAM system. Well, imagine that I was like trying to train a perception model that was gonna like do semantic segmentation. In other words, it was gonna like assign every pixel in an image a class corresponding to the thing that it is. Well, now because I can backpropagate through my entire SLAM process, I can regularize that over the actual like true 3D geometry of the world, right? So there's some really nice benefits to being able to do this. Very few of which we actually showed in the end. We just sort of like, we're assuming that people would do it, but they haven't really. Okay, so this is like a bit the idea. So here we have, let's say like a 3D map. We have a 2D image that's coming in. And here, for example, we just added, like this 3D map's already been built. We add an occluder to this 2D image. And we show that like this generates, it's like hard to see. It generates a gradient that we're visualizing in image space that shows that like the error from that image is being created by the occlusion that's being added, right? So this new occlusion that we artificially added into this image is generating some kind of inconsistency compared to our 3D map that we already have. And so we can like pass that gradient back to the image, and then we can do whatever kind of feature learning that we want on that. So here's maybe a visualization that's a little bit easier to understand. Okay. Okay, so yeah, so maybe the point of this part, A, is just to like show this thing that I think is cool. And B is to say like, we don't necessarily have to have this dichotomy between explicit and implicit representations. In fact, we can have parts that are learnable and parts that are not learnable. And the tool that we really need in order to be able to connect all those parts is just to build like differentiable connections. So as long as we can build a computation graph that's composed of differentiable parts, then we can move gradients around from the parts and learn feature representation. Okay. Okay, so now let's talk. I think this is like my favorite part. So we'll talk about semantic representations, what I call. So I'm going to talk about two papers, one that was published at RSS last year and the one that's under review at ICRA, which I'm allowed to say because ICRA is only single blind for some reason that nobody can understand still. Okay, so this first work is called ConceptFusion. So the idea here is, I mean, ideally what we want, a property that we want inside our representation is not just geometry, but also semantics, the underlying semantics of the objects or things in the world. And we're like by no means the first person to think about this, right? This has been an idea in the SLAM community for at least a decade. So here are some really sort of important examples. I guess the first maybe it was Slam++, which came out of Andrew Davison's group, which was just representing objects inside of a factor graph style thing and optimizing them, right? You have problems like the higher you go in terms of semantics, the more you have challenges in terms of aliasing, because like there's some inherent ambiguity with respect to like, is that the same chair as that chair? They look the same. So I need to do some joint reasoning over semantics, but also geometry. And then there's these other works, semantic fusion, and then this, which is a scene graph representation, which I'll talk about in a bit more detail later. Okay, but the problem that we identified here is that these all are closed set, which means, so they all require an object detection module at the front to do the first piece of detecting the objects. And so we have like deep learning based object detection modules. But these ones, they all have a fixed number of types of classes that they know about, and they can only predict the existence of those objects. So they'll, by definition, they will all fail in an environment where there's an object that it does not correspond to one of the classes that the object detector was trained on, right? And secondly, there's sort of, there's a limited number of queries that you can actually make over these maps. Like, okay, yes, you know that's a chair, but that's somewhat informative, but you still have to do some sort of post-processing at the planning stage to figure out, okay, it's a chair, what can I do with a chair? How do I actually use that for planning to like leverage the properties of a chair? Okay, so, I mean, unless you've been living under a very big rock for the last 2 years, you've heard of like large language models, at least like ChatGPT. Okay, so that's not something probably brand new. And unless you've been living under like a slightly smaller rock, I guess, you've probably heard that there's other types of like large models that are now coming out that are like, that cross modalities. So what I mean by that is they take two different types of modalities, in this case, image and language, and they find a joint embedding space for those two modalities so that you can sort of like go in either direction. I'll explain what I mean by that. So this example is clip. It's probably the one that really sort of like blew everybody away about, I don't know, 2 years ago. So what is this thing? So they leveraged an internet scale of data of images that are captioned. So you can just crawl the internet and get every single image out there that has a caption associated with it. And so you can imagine that like for each captioned image, you have like an association between the text and the associated image, right? That these two things should go together. Okay. So what you can do is you can, use like your favorite fancy encoder and take this image, pass it through a vision encoder, let's call it a vision transformer, take the text and put it into a language transformer. And then what you're going to do is you're going to enforce that these two things, if they correspond to the same thing, are close in embedding space. And if they don't correspond to the same thing, that you push them away in embedding space. And so for those of you who know about this kind of thing, this is a contrastive objective, right? So we're just going to take the matching pairs, and enforce that they go close, and take everything else. And so that's really all there is to it. So they take this ginormous data set of internet scale data, and they put it into batches of like 32,000, of which there's only one corresponding pair. And then they generate a loss that says, well, like if you predict the right corresponding pair, we'll push those together, and everything else is going to get pushed apart. So that's sort of what this picture is showing. You could imagine that there's like a whole bunch of captions, a whole bunch of images, and you could generate a big matrix of distances between those embeddings. And you want to enforce that the embeddings down the diagonal, that the distances down the diagonal are small and the distances off diagonal are big. Okay. But the cool thing, so once you got this representation, the cool thing is that you can actually use it for like so-called zero-shot prediction. So like, imagine now I've got a new image that I never used in the training set. I can generate a bunch of kind of weird text queries, like a photo of a whatever I want. And then I can see how well they match in the embedding space. And so by virtue, like even though I've never seen even I have no real concept of what a dog is, and I've never seen this picture before. If I show the thing this picture and I generate a text query that's a photo of a dog, it's going to be closer, that text query is going to be closer than all the other, a photo of a whatever, fill in the blank. And so I can like infer that this is a dog. Okay. Very cool. Another model that we've leveraged exclusively is this, or extensively, is the segment anything model, which came out of FAIR, which is basically a sort of a new approach to unsupervised image segmentation. I'm not going to go through the nitty-gritty details of this, but you can imagine that this thing is now able to generate contours around objects in an unsupervised way, and it generalizes extremely well. Okay, so given those, so now we have these two tools out there that are like available for us. By the way, like the majority of this work, it's like engineering. There's not like a lot of math involved. So what we can do is we can, the objective, what we're going to do is we're going to do the same thing we did before to build a nice dense SLAM map. But now what we want to do is associated with each point, we also want to tag the embedding that would come from one of those big vision language models, right? And so the cool thing if you do that is that now you can actually query the map using this other type of modality. So, and the amazing thing, I think, for me, that's very surprising, is you can give text queries that are like relatively abstract. It's not like a text query has to be like a TV, you know, it could be like something, somewhere comfy to sit and watch TV, right? And it just so happens that in the embedding space, the closest points to that, the embedding of that text in our SLAM map will correspond to places like couches and chairs, right? It's like magic, really, right? There's other modalities that you can also do this with. So we can also do like audio queries. So we can like just input like wave files and it'll tell us where things are that are associated with that sound. We can also input images and it'll show us other things that are like that image. So, you know, what looks like, and you show a picture of a table and it'll show us all the tables. We can also click on this map and it's interactive. You know, it can show us anything that's just like the thing that we clicked on. Okay. So in summary, we have this thing called ConceptFusion. I'm going to explain a little bit about how it works, but the like punchline is that we now have built this representation that we can query in these like multimodal ways, which I think is pretty cool. Okay, some more examples. Text queries over 3D scenes like sofa. These are easy. We can give an image, a picture of a plant. It's hard to see in this thing. This one, I don't know if there's sound. There's like a door knocking sound, which you can't hear. So it's not much use. Okay, so how does this thing work? And I mean, it's like, again, I said it's like mostly engineering. So the main problem that we have, sort of the only, maybe there's two problems to overcome, okay? The first is that Clip, for example, wants entire images as its input, but we want to represent embeddings on individual points, right? So it wouldn't make sense to take every point associated with an image and give it the embedding that was generated by Clip over that entire image, right? That's not necessarily like fine enough resolution to give us a really good like semantic understanding of what's at that point. So what we do instead is we take the image, we pass it through Clip, and we get what's called a global embedding. So that's the embedding of the entire image. And then we take that unsupervised segmentation network and we generate little masks around things in the image, basically draw bounding blocks around that, and then send those things through Clip as well. And so for each one of those, we get a local embedding, okay? And we can figure out which points in space are corresponding to which local embedding and which like in the image and which by like back projection or whatever. Okay, so we have this image. We find the masks with this segment anything model. We crop them. We pass them through a feature detector, and then which is the Clip visual feature detector. And then we do some kind of fusion between the global and the local embeddings to give us an embedding for a specific point that is best at encapsulating the semantic information. And this is like a bit heuristic, but more or less, the idea is if you take one image and you look at all the local embeddings and you look at the distances between them in embedding space, a lot of them are going to be very close because it's the same image, but then a few of them are going to be far away. And so you want to somehow, for the ones that are far away, they probably are encoding some kind of particular small thing inside of an image as opposed to the concept of the entire image. And so you want to sort of upweight those local embeddings for the ones that are particularly unique, right? So yeah, so basically you just look at the cosine distance in the embedding space and you do some kind of weighted average over the similarity between the global embedding space and all the other features that you found in local embedding space. Like there's no real great theoretical foundation for that. It's just like an intuitive like thing that works relatively well. The other thing is that because this is SLAM, right, we could have lots, we could view the same point in space many times. And so we need a way of fusing these embeddings. So like we know how to do that with geometry, but now we need a way of fusing this with like fusing these semantic embeddings. A very simple way to do it would be to just do like a running average, which works okay. We found that if we add some kind of like confidence score over this embedding, which is mostly by virtue of where the point sits in the camera frame, that we get more robust fusion of the feature embeddings. But then more or less, so like over time, as we see the same points over and over again, we just fuse the embeddings, both in geometry and in the semantics. And then we end up with this map, and we can do this whole fusion thing with this grad slam thing that we talked about. Although we don't really leverage the differentiability of grad slam. It's just sort of like nice to say we used our own thing. So there's lots of sort of cool things that I think that are pretty difficult to do with other methods that we can now do. So one is like joint reasoning over geometry and semantics. So like now I can write a text query, which is like what's the distance between the refrigerator and the television? That's not so simple, right? So now we need to find where the television is. We need to find where whatever the other thing is, refrigerator is. And then we have to go back to the geometric representation and actually look how far those things away. So that's cool. We did this with some car experiments. This was in Singapore, actually. I mean, basically anything that's a point cloud, you can just embed, like add this embedding. And so now we've just we show that, whatever the concept of roundabout is well understood by the embeddings in this like HD map for a car. So you could now give text queries like go to the roundabout, and it would just query the map, find the roundabout, and then find the embedding in the 3D map that's closest to roundabout and then go there. What else do we have? Oh yeah, and we also showed some interesting kind of very simple tabletop manipulation experiments where now the way that we can specify the task is still relatively abstract, I would say, move the caterpillar to the left, move Baymax to the right. And the cool thing here is that there's never been any labeling of what's a Baymax or a caterpillar in any kind of explicit way. There's just sort of some reconciling of what those things are and then how we have to operate the manipulator in order to satisfy the query. Okay, so that's ConceptFusion. Okay, so there's kind of one major problem with this approach, and that's that these dense methods, they just don't scale. It really doesn't scale beyond a tabletop environment. Luckily the HD map is relatively sparse, but loading this whole thing in memory, even a room-sized thing, it's all on GPU, and you just you run out of GPU RAM no matter what, even if you have the fanciest NVIDIA GPU. Right, so this doesn't scale. And there's also I think there's something else that's missing in the previous representation, is that we don't have any kind of way of really representing relationships between semantic entities in the previous representation. So, by the way, I didn't bring any clock, but oh my. Okay, super. Okay, so what we're going to do is we're basically going to take that last approach, which was a dense 3D representation. And instead, we're going to try and like break that apart into a sparser sort of graph-based representation. And so for this, we're going to leverage what's called the scene graph representation, which has been pushed by several people, including like Luca at MIT. And it's like, I think, intuitively very elegant representation. So the idea here is that you predefine some kind of hierarchy of things. So at the top, the most abstract thing would be a building, and at the bottom, it's some like mesh point cloud or whatever. And then you have these intermediate representations in between. And what you're going to do is you're going to like, as you're navigating around the environment, you're going to be able to perceive these different entities, and then you're going to be able to like establish relationships between them. And pretty much the only rule, I think, is that entity relationships can only go either among entities on the same hierarchy or up or down by one level and no more. So you can't say that, you know, this object is inside this building. You have to go through, okay, it's in this place, this room, okay. Okay, so this is nice. There's been some really nice work that's come out. I think it's an intuitive representation. Like there are some things that are maybe unappealing. It's like there is a very hand-engineered kind of hierarchy, and maybe you could learn it, or I don't know, whatever. But intuitively, to me, it like makes sense as a hierarchy. But the relationships between these entities, first of all, you end up with like very, very dense relationships, because everything, if your relationships are mostly geometric, at least at one level of the hierarchy, well, you can establish a geometric relationship between, like exhaustively between any pair of things. It's not that useful. And even going in between hierarchies, the relationships that you tend to see in these graphs are relatively primitive. And by that, I mean, it's like, okay, this object is inside this room or whatever, right? They're mostly, if they're not purely geometric, they are, you know, basically geometric. Okay, so our objective is we're going to take the ConceptFusion idea and we're going to try and plop it onto this representation. So I only have one slide to describe how we did this, and then the rest is just all results. So let's try and go through it slow. So I should have made this appear slower, but okay. So on the left, we have the input. You just have an input RGBD sequence. We're going to do exactly the same thing as we did last time. We're going to pipe it through like one of those unsupervised segmentation models to get all these segments, okay? And those are going to give us some kind of like object proposals, okay? We can then pass these regions that we detected through the unsupervised segmentation model through CLIP or whatever vision language model to get like embeddings of these individual objects that are detected in this image. And then we're going to do some kind of like fusion process. So ultimately what we end up with here is like these objects have there's small point clouds associated with the object, and also some kind of semantic representation. And then we can do some kind of like object level association, which is basically a nearest neighbor search that operates jointly over the geometry and the semantics. So like, we are only going to say an object is this that we've seen here is the same as one in our map if like it's close enough in space and it's close enough in terms of its like CLIP embedding. Otherwise, we're going to say it's a new object. So at the end of this phase, we end up with a bunch of objects all fused together. And that's our map. It's now a completely like object-centric map that we can generate. Okay, so now is the fun part. So now we want to generate the relationships between these things. Well, so the first thing we can do is we can actually generate some kind of like semantic textual representation of what that object is. How do we do that? Well, we can take a bunch of the images that we actually use to, like, or a bunch of the cropped images that we use to find that object, and we can pass them through an automated like captioning system. And let's say we take the 10 best, the 10 ones that seem to be the like most confident about the semantic interpretation, and we just pass those through an automated node captioning system, and we get 10 captions for this image. Like, this is a plant, this is a green plant, this is a plant in a pot, blah, 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 blah. Okay, so we take those 10 captions, and we can actually like take those and just pass them to an LLM and ask it to summarize them for us. So we take those 10 captions and literally generate a query that says, summarize these 10 things for me, please. And it generates one caption that's like a summary of the 10 captions of the 10 best views that we've seen it. And so at the end, when we get our object map associated with each object, we actually have like a textual representation as well. This is a whatever, 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 which was generated by this combination of the node captioning system and the LLM. And then to generate the connections in the graph, well, we can just use an LLM again. So we just take like the summary of one object and the summary of another object and combined with their positions, and we ask an LLM what it thinks the relationship between those two things is. So for example, here we have like one object is a stool, and we have it that it's in position 22, 23 in our map. And another one is a carpet with position on the floor or whatever. What's the relationship between 1 and 2? And the large language model is going to tell us what that relationship is. Well, it's most likely that the stool is sitting on the carpet. And so that's how we can generate these edges. And now actually these edges, because they're like generated by these large language models, can be much more rich and descriptive than the sort of primitive geometric based edges that we had in the sort of previous methods. So now we can just take this 3D scene graph thing, and we can do all sorts of crazy planning over it. We can do navigation, we can do all sorts of stuff. So I'll show some fun examples. Any questions about how this thing works, more or less? Yes? No? Okay. Okay, so easy stuff we can do is like semantic localization. We can just take a particle filter and we can like localize based on the semantics. This I think is like pretty trivial, actually. Not so interesting. But some of the text queries that we're able to do, to me, like I think are amazing. So this one goes a little fast. Let's just go to the next one. So here the text query is something that goes well with a Ronald McDonald. So we've already pre-built the scene graph for our lab. This is my lab in the University of Montreal. And we've put some weird stuff around. Like, okay, it's like maybe you know, bit of grain of salt, like a bit cherry picked, or whatever. But nevertheless, I still think that the fact that like it's able to actually execute on any of these is tremendous. So something that goes well with a Ronald McDonald outfit. So it drives and finds these red shoes under this desk. I think it's pretty cool. Seems reasonable. Let's see. We also have this because it wouldn't be without a ducky. It wouldn't make sense. We have this, the move the cuddly quacker to the next thing or something. I forget what the query was, but there's no mention of a ducky. And so this thing can figure that out. It needs to have the actual skill primitives to be able to execute the specific task, but that's for another day. We can also handle like combination of text and image queries. So this is the robot is showing something. Maybe I'll just slow it down. Okay. So let's run that one more time. So the text query is something this guy would play with plus the image of Michael Jordan. Okay, and it finds the basketball. We can also specify language written but interpreted through visual input. So it's just sitting in front of a sign that says go to the laundry bag. And so it has got to just, like, it's not doing OCR or anything. It's just like the embedding of that image happens to go closest to the laundry bag, which it drives to. And then one that, this is also, I think it's very, very cool, but also should take with a little bit of a grain of salt. There was a little bit of extra engineering that was done here. But you can do some primitive inferring about object affordances. So what's going on here is, it's like hard to pause. Okay, so the robot has to do a navigation task, but it's blocked by in all of the various paths. But the various paths are blocked by different objects, some of which you would intuitively consider to be traversable, like cloth or a ball, and others which you would consider to be not traversable, like a brick or a plant or something like that. And so without ever actually explicitly encoding the notion of traversability, the robot is able to find that the navigation path that's most likely to succeed is the one that goes like, instead of trying to go through the desk, it tries to go through this cloth, and then you'll see it tries to go through the like, of these three options, it picks that ball to go through, right? Maybe one other thing that I'll just go back onto one slide that I skipped. So just a little bit about how we're actually doing the text queries. So there's sort of like, there's two ways that we've experimented with. The first is sort of exactly the way that I talked about before. So imagine you have a text query, you find the clip embedding, you look through the map, and you find the closest object to that embedding, and you go there. The other thing that we can actually do is we can encode the entire scene graph as text, because it's just a textual, like, with all of the node captions that we've generated. And then we can like just encode it as a JSON file, and then do the actual text query purely over text, like where we give it the JSON file according to the scene graph and the textual input. And that actually, in most of our experiments, proved to be more robust. So this goes too fast, but that's sort of what's being explained here. So something to go to a space theme party. And so there's this NASA t-shirt that's sitting on a thing. And so that's with the clip embedding, and then the LLM version with the with encoding the scene graph as a JSON file is also, I thought there was another example, but anyways, there's one that we show where the clip embedding fails. Okay, so that's this thread that we've started in our lab about using these vision language models to build SLAM graphs that have these kind of like semantic embeddings. By the way, like this, we're not the only ones trying to do this. This is like super hot right now. I think part of the game here is like being fast, you know, like the ConceptFusion paper, we got it out like super fast because we kind of had that whole grad slam thing already ready to go. It didn't take too much tweaking. And I have a ex-PhD student who's at MIT now, who's just like incredibly efficient with implementing these pipelines. But there's it's a whole burgeoning field of work of how to leverage the intuitive understanding in these large models to good effect for robotics. I mean, I think that I have lots of ideas, but like there's a lot of work in this area. Okay. Can I get a quick time? 10 minutes. Okay, so maybe I'll go a little fast through the last part. So I put this last part at last because I think I was worried I would run out of time, and it's a little bit less exciting. But anyway, okay. So let's see. So another idea could be that, like, okay, if we want to do things like navigation, maybe a dense, you know, like let's say like the normal workflow, if you're in the DARPA Urban Challenge, I guess, or whatever, would be that you have to like generate that like representation, your configuration space, right? And then you pass your configuration inside the workspace to your planner, and then your planner does some planning inside that configuration space, right? Correct me if I'm wrong. Sounds about right. Okay. So that step of having to like construct that configuration space, like kind of annoying, right? Like you need a pretty dense representation in order to be able to like query it with RRT or whatever like that, right? You need like a denser geometric representation. So I guess the motivation for this work was like, okay, imagining that we're using images, like, can we skip that step? Is there any way that we can like skip the actual generation of the metric representation that we actually have to plan over? So I guess that's the motivation. So the proposed solution here is like, so imagine like you have a robot and it shows up at your door, and what you want to do, okay, is you want to like just walk around your house with a camera, you know, take a video of your whole house, and then download that data to your robot. And then you want to be able to just like show an image to your robot and have it be able to navigate to that place inside of your house. Let's say that's the task that we want to do. Okay. So the idea here is to kind of do like something pretty akin to like a probabilistic roadmap or a sampling-based planner, except directly over image space. So what we want to do is we want to construct a graph where the nodes in the graph are just images, and the edges in the graph denote whether we can reliably navigate between those two images, okay? And so the model that we need for that is this model that sort of tells us if we give it two images, whether we can navigate between those. And so that's a model that we train in this case. But you could think of even doing it in other heuristic ways using like visual servoing type metrics or something like that. Okay, yeah, and so the bonus is now that instead the other inconvenient thing with something like RRT or any of these type of planning methods is that you have to specify the goal in some kind of frame that the robot knows about, and usually that's difficult. That requires like measuring things. Okay, so I'm going to maybe skip a little bit quickly through some of the details, but the sort of crux of the whole method here is this reachability estimator. So what we want is we build a neural network model that takes as an input two images and outputs either false if we can't navigate between those two images, or true and the relative waypoint between the two images, or the homography basically between the two images. Okay, and so we basically trained this thing in simulation with like a whole bunch of weird heuristics. So I'm like really leading with like what's the crappiest part of this work. But like, so, we basically generated a labeled data set in simulation in Habitat or whatever that had pairs of images and then the respective transformation between them, which we have because it's in a simulator. And so imagining that we have this model and that it works well, the rest of the workflow I think is pretty nice. So you have this whole big bag of images. And the first thing you have to do is you have to construct your graph. So you just start sampling images. You start with the first, and then you pull the second, and then you ask your reachability estimator if those two things can be connected. And if yes, you connect it and add it. And if no, you put it back in the bag and pull out another image. And you keep going until some kind of stopping criterion. So it's like, I think really pretty reminiscent of something like a probabilistic roadmap, where you're just sampling configurations in a configuration space, and now it just so happens that the nodes in your graph are images. Okay, and then you assume that you have some kind of controller. Once you've determined that two images are reachable, you have some kind of controller that's going to be able to take you from one to the other. This could be just visual servoing. It could be some other kind of it could be reinforcement learning if you really love reinforcement learning. It could be some other thing, right? And so that's sort of the workflow of this approach. We build the graph, and then when we want to do the actual planning, your new goal is specified as an image. You try to connect that image to your graph. You find a path through the graph to the goal, and then you just navigate the edges one by one until you get to the goal, or you fail. Yeah. So the other aspect of this is that, if you fail, we have some kind of Bayesian statistics over the edges. And so if you try and navigate an edge and you fail, then that constitutes some kind of like failure that we fuse in the Bayesian set. Okay, so we showed that we can do this in some simple environments. So these are all like simulated environments. So maybe just to explain what's going on in the picture. So at the bottom right, you see like a top-down view of the environment, which the robot has absolutely no access to whatsoever. It's just for visualizing. And then in the top right, you see like the next sub-goal in the graph, which is just the next image that it's trying to navigate to. And then in the top left, you see like the final goal. And so as it goes, like maybe this one will go, you gradually see the new sub-goals changing as they get achieved, until the sub-goal and the goal are the same, and then you've reached the goal. Okay. We also did this on a real robot. We used this weird locobot thing. We have sort of some simple experiments in relatively small environments. So like these are not navigation experiments that I think are gonna like blow the world away. Like it's a very small environment, et cetera, et cetera. So, okay. And maybe, so there's some inconveniences about this particular approach. If there's no questions, there's some inconveniences about this approach. First of all those heuristics to define reachability are really bad. In practice, we required fine tuning on the target environment for that reachability estimator. And so we actually, we proposed a follow-on work that was published at IROS this year that basically like, you know, I'm in Mila, right? So everyone just wants to do like machine learning for everything. So this is just like, let's just put a neural network everywhere, basically. So I'll try and explain, I can explain what's going on here. I can go step by step. So it's the basic setup is the same. We get 2 images at the input and we have some kind of reachability estimator, except instead of all those heuristics that we had before, now we just use what's called a time contrastive loss. So it's the same thing like we talked about before, except we're going to use like 2 things that are close in time as being a matching pair, a positive, and 2 things that are far away in time as being a negative example. And then we're just going to like just try and push the things together that are close in time and push the things away that are far in time. And so everybody usually asks here, like, okay, like what if you do a loop? And it's like, yeah, I guess that would be a false negative, but somehow these models, it's just like, it works out in the end. It's like, if you had a data set that was just driving around in circles like forever, that would be a problem. But in a reasonable data set where you're not like doing the same path like over and over and over and over, there's enough true positives that your like false positives get outweighed. And so at the end of the day here, we end up with, the same thing. We end up with this model that can predict like this embedding space, okay? And that we can use, that we can sort of interpret. Not exactly. And then we have the second model, which is an inverse kinematic model, which takes 2 of these embeddings and does the reachability prediction. So this thing outputs either not connected or what's the action that you should take to get from one to the other. Okay. Then, so we can use these 2 models just like we did last time to make a graph, okay? But we can also add new edges to the graph using this other model that we train, which is effectively a forward kinematics or forward dynamics model, which basically just takes an action and an embedding or an image, which it gets embedded, and then predicts the next embedding. The embedding that you would go to if you're embedding xi and you took action aij would get you to embedding xij. And if that thing ends up being close enough on the graph as something that's already on the graph, then we can just connect those things. And then finally, instead of actually searching the graph, we trained a neural network to do that for us. So we call this thing a geodesic regressor. So we just give lots of queries of starts and goals, and the paths associated, the correct paths. And then we train a neural network that just actually predicts the geodesic distance between these 2 things so that we don't actually, at the end of the day, we can just give the start and the goal and throw the graph away, more or less. Okay, so at the end of the day, we throw these things away. And what we end up with, like, okay, so now we get into like professor conjecture, not substantiated by fact part. Okay, what we sort of get is like an embedding space that we get something like a manifold that represents the free configuration space. And the nice thing, if that's true, is that you can do very, very simple planning on this embedding space because it doesn't have any holes or local minima, right? So our planning ends up being, in this case, just potential fields. But I'm over time. Sorry. Okay. So, in Euclidean space, this is like a very ugly local minima. But what we sort of see is that the manifold that we learn, it doesn't have this local minima. It understands the configuration space, and you can literally just like walk downhill in this like Euclidean space and get to the goal without ever hitting any local minima. And so we set up this sort of potential fields planning where there's an attractor at the goal, and every configuration you've already been to, we like leave a trail of small negative repulsions, so that it's like when your kid turns 18 and you need to get them out of the house, like just a little bit of something to get them going. Okay, and so like here's some visualization of these manifolds, and these are PCA projections or whatever. And like I would argue maybe that like topologically you could see a relationship, between this manifold and the actual free configuration space of the environment, maybe. Okay. And so we did experiments with this, and it like also pretty much works in similar ways, but has nicer properties than the previous because we don't need to do this fine tuning thing and we don't have these ugly heuristics which make it brittle. Okay, conclusions. Representation is key. We have some new tools that have come out from the large language model community that are interesting, that we should think about how we can actually use them for robotics representations. In my opinion, the types of tasks that, certainly in our case, but also at large in the robotics community, the types of tasks that were I don't really feel like I justified the title of the talk, because the complexity of the tasks, I would argue, is still relatively primitive. And then I have some thoughts about better ways that we can improve the representation, but I think it needs to be more conditioned on the specifics of the robot. Sorry for going over time. Thank you for your attention. This is my group.
Questions. So for the remote audience, you can post your question in the chat, but are there any live questions?
Neither. Oh, yeah, need the thing.
So that the remote people.
Okay. Thanks again. It's a really fascinating presentation. I just wonder, when I listen to the thing that you're doing is up to what point what I'm teaching in class, it's completely worthless, right? Because now we have all these new methods, right, of doing things.
Teaching what? Teaching?
So I'm teaching this planning, decision-making course, right? With
Yeah.
all those RFTs and things. And
I mean,
wonder up to what point, we wake up tomorrow and that's completely worthless. But no, the question.
okay, well, that's not the question. That's just sort of
That's not the question, right? So the question is, for example, you made the parallel with a PRM, right? And building these roadmaps. It seems to me, if I understand correctly, that a lot of the work that you're doing with this representation are mostly geared towards, say, a stationary environment, right? So, for example, if you say, okay, so look for the NASA shirt, but you happen to move, or somebody moved the NASA shirt, what happens? So how do you update, or how do you work in an environment that maybe you've not seen before?
Yeah, it's a great question. It's really, I think, we're working on that right now. I can tell you what happens right now. So what's easy is to do a query look for the thing for the space party, and you go where the last place you saw the NASA shirt was. And if it's not there, you just look at the next closest thing and you go there, So we have examples where, for the Ronald McDonald one, for example, where you go and look for the red shoes where they were last time. You don't see the red shoes, so you go to the shoe rack after. Maybe that's reasonable, but it doesn't solve the problem that you're talking about. No, I believe that this is still a massively open question, that we don't have the right representations to encode time varying properties. There is work, particularly in the old work in the SLAM community, and also newer work on trying to address these things. But ideally, you want a representation that that you can actually do inference not only in space and semantics, but also in time. But yeah, we're not there yet, or at least I'm not. But it's very much a central question that I'm trying to address.
Well, in the example, what if I happen to find the NASA shirt in a place that I did not expect to see? So I'm on my way to the last known location of that NASA shirt.
Yeah.
In the CNS of shirt.
I would say it wouldn't be difficult to update the system to actually look at the live feed and also compare the embeddings from the live feed and see if they satisfy the query. I don't think that would be, we aren't doing it, but I don't think it would be super difficult to do. So you could imagine you get the query, you look at your map, you have your best guess. And then as you're going, you're also querying every single image that you're getting to see if it's even better than what you thought, or you're live updating your map at any rate. These things run, the updates are pretty efficient, actually. It's not insane, to do these updates, to like query these big models. I mean, you need lots of GPU RAM and like, but it's not like you'd want to put it inside a real-time control loop. But for something that is like at the planning level of abstraction.
One way that I introduce, like PRM versus RT, that PRM is, I think of it as a multi-query.
That's right. That's why I would argue that this is more close to
so versus the RT, which is more like single
being grown as you
grown,
yeah.
Right.
Yeah. So in that case, like in the later work that I was talking about, the topological navigation, it's very much that way. We take the bag of images that we have, we construct the graph, and then we do many plans over this. It also, I mean, I have this sort of feeling that there's also like, what we should be optimizing is the ability of a robot to operate in one environment over a very long period of time. That's mostly what we want, as opposed to this idea that we want super generalist robots that are able to do anything in any environment. I'm not sure. Yeah. But so what I want to build is the tools so that like we have lifelong learning over one very relatively constrained, like a household size environment that you learn over time. This is where the things normally are. Guy wakes up at this time, girl wakes up at this time. Don't go in there at this time because she's in the shower. Like these are like the intuitive concepts that we could build over time about the like spatial and time and semantic concepts inside of an environment. Yeah, so this, I think this is a very, very interesting avenue for future work.
Thank you. I just want to give other people some time.
Any other question? If not, there are two from the chat.
Yeah.
There's Andreo Jimenez who asks, how do you go from task query to the low-level control? For instance, in the context in which you have combined motions of or complex tasks, you might need some way to do that. Or is he's asking also, are those controls handcrafted?
So it's a great question. So like I can talk about the specifics of any of the projects here, but for the most part, we're kind of assuming that the low-level skill is something that's more or less provided for us. And so like, for example, in this work, we assume that the robot has some kind of policy that it can use to navigate to a waypoint in space. I think in that example, it's very reasonable. A simple controller can do that. But what I would argue is like in the more sort of complex, like scene graph-based stuff, yeah, what we want is like those edges shouldn't necessarily even just encode relationships between things, but they should encode like what is the skill that my robot needs to execute in order to achieve that, the transition over that edge. And that's kind of what I mean when I put in my future work that like these representations should be like robot conditioned, is like there shouldn't be an edge there if my robot can't do it, you know? And that could be at any kind of like level of abstraction, right? Like, you know, but so the short answer is for the vast majority of our work, we've used one policy that we assumed that the robot sort of already had, whether it's the manipulation work or the navigation work, it's something that's given. But I think a very interesting avenue of future work is extending this to actually infer what skill you should execute and then like embed that inside your representation. This is a great question.
Okay. Okay, there is a follow-up question from the same person actually. Do you think these representations could be useful for planning of long horizon sequential tasks? It seems that planning in the examples involve a single task to goal. However, if a sequence of actions is required, maybe the relation between the options in the scene would change. I think this is something to what Emilio asked.
It's very related. Like, so I think it's a step in the direction. Like, I think that but it's not there. We're not there yet. Like, still the assumptions of even these scene graph type models, there's assumptions of relatively static things, and that there's no, the compositionality of tasks is difficult. So I think I have some ideas here, but this is really what we're working on right now. Is like, how can we like again sort of like reinvent this representation so that it can exactly handle those kinds of situations.
All right. Thank you very much, Liam. Any other question? All right. Let's thank again Liam for the great talk.
Thanks so much.
And thank you, everybody from the remote audience. See you all actually in 1 hour for the next talk.